Our discussion here will be understanding semiconductors. Now, we're not going to turn you into electrical engineers or electronics engineers, but a little bit of understanding on how these components work will lead to a lot of understanding as to why we have a more efficient light source with LEDs. Start the discussion, we really want to understand more about types of power and also the AC and DC and also about types of diodes. We're really only concerned about two types of diodes, even though there are many types of here. We want both a basic diode and a light emitting diode. When we consider aluminum copper as conductors, aluminum is usually used in the transmission of high power over long distances because the aluminum product is strong enough to be able to string it over long distances on high power lines without having multiple towers to support it. And even though aluminum is less efficient of a conductor because of its high resistance, if we step up the voltage and step down the current, relatively speaking, the losses aren't so great and aluminum becomes an ideal product for high power transmission. Copper is certainly more efficient, but because of its weight, you need to have 3 times the number of towers, and it would be 3 times as expensive for the basic wiring, and so that wouldn't make sense to use copper in high power lines. Or long transmission lines. But both aluminum and copper are considered conductors. And as conductors, they allow electron flow in any direction, which is exactly what AC or alternating current power is alternating current is power that swings from negative to positive to negative to positive and continually back and forth. And when you use the power generated from that electrical flow to then drive motors, air conditioners, all kinds of equipment, and we can convert AC to DC relatively easily. DC, direct current, is the typical type of power that you would think of as being supplied by a battery and in smaller electronic devices that we use day in and day out, handheld devices. To understand how this is done, we need to understand the basic makeup of a diode. Take a common diode, which is a silicon diode. And silicon material has 4 electrons in its outer orbit, which means we can have as many as 18 in that orbit. So there's a lot of room for electron activity to take place, a lot of room for electrons from neighboring atoms to flow to these components and create conductivity. But we've got 2 blocks of silicon here because if we just use silicon and put wires on either side, we have just another component in there that was adding to the conductivity in both directions. But a diode doesn't do that. If we take silicon on one half of the component and dope it with arsenic, we laden it with more electrons. If the other side then, we remove electrons from that elemental structure that's there, we create what are called holes or positive potentials for the electrons to move into. And what happens is when we bring the 2 materials together, because of that potential difference in the electrons on the arsenic doped side versus the electrons on the boron doped side, there's an area where the 2 are combined called a depletion zone or a barrier region, and this is what makes the diode function in the fashion that it does. Because if we put power to this component in the proper fashion, we have conduction. If we put power to it in reverse fashion, we have nothing. Nothing takes place. So if we apply power to this in what's called a reverse bias direction, that depletion zone, that barrier region, essentially expands and electrons can't get across it. So we have no flow of electricity, no conductivity. If instead we apply it in the other direction, then we have electron flow and we have conduction taking place, which is the reason that a diode is called a semiconductor, is because it's only conducting electricity in one direction. Now, the advantage to this when it comes to its use as a diode, not necessarily an LED yet, but as a diode, is that it allows us to convert things electronically. So if I take alternating current, which is swinging from positive to negative and doing so at either 50 cycles per second in Europe or 60 cycles per second in the US, swings positive to negative, I can chop that waveform up because the diode's only going to allow power to flow through one half of the cycle, only through the positive half. I add to that diode another component called a capacitor, which stores electricity, and it can store electricity for microseconds, milliseconds, seconds, minutes, depends on the size of the component. Then as the power rises, the capacitor charges up, holds that charge until the next rise in power, and the next rise in power, and we effectively then can convert the alternating current into direct current because we're ignoring half of the cycle and we're storing that electricity up within the capacitor itself. And that's how a diode functions. But let's go back to an LED and what's happening in that. Again, I have the silicone with the doping of arsenic on one side, with the doping of boron on the other side, creating the depletion zone in the middle. And if I forward bias the unit properly, I'll get electron flow across the LED, across the diode, in the case of an LED, across the LED. And as we know, when the electrons from one atom move to the next, if they stay in the same orbit, they don't release any power, they just continue to flow. But if they drop to a lower orbit in that atom, then they release that spent energy as a photon. And photons are emitted only when the electrons settle into a lower orbit when they move or when they conduct to a neighboring atom. And this is the key to understanding the efficacy of LEDs. The greater percentage of electrons that produce photons, the higher the efficacy of the component. And when we do this electronically by creating conductivity through electricity as opposed to conductivity through heat, we have a more efficient system. Now, understanding semiconductors, we do have to understand both thermal and electrical conductivity, because heat does create electron energy and thermal conductivity, and electrical biasing creates electron energy and flow or conductivity. But let's deal with the heat portion of it for a moment. Why is heat less efficient? What does it do? What are the drawbacks there? Well, though the thermal conductivity will create more electron flow, and if you take and heat up a piece of metal, you can get it white hot, you can get it red hot and white hot, but it's a very, very inefficient way of doing that because the percentage of electrons releasing their energy as photons doesn't increase, but drops rapidly. The percentage drops rapidly. The reason for this is that when you heat up atoms, they vibrate. That's where the heat comes from, is its friction between them vibrating together, and they expand and separate from each other. And as a result, you have a greater distance for the electrons to flow. The electrons don't necessarily combine properly with the neighboring atoms, and so you don't have good photon production in this scenario. However, we consider both thermal and electrical conductivity. If we consider the electrical biasing creating electron energy and flow or conductivity, then we get a much higher rate of conduction or conversion of electron energy to photons. Because when we apply the electrical energy to the conductor and imparts the energy to the electrons, that's where you get your flow or conductivity. More power means more electron flow, but we need to have the electrons drop to a lower orbit when they do that in order to produce a photon. And they're more likely to do this when you're doing it with strictly electricity because they impart the power to it and they drop to a lower orbit, and some continue to flow on through to produce electrical conductivity. And understanding this process, understanding LEDs, considering both thermal and electrical conductivity, helps us to appreciate where these efficiencies come into play. Because keeping LED drive currents down creates better efficiencies because the electron orbital conversion that creates photons does so at a higher percentage rate when the drive current is lower. Because we energize the electrons too much, then they skip that process of dropping to a lower orbit and creating a photon. They just flow straight on through as electricity. So there's a balance between how many of them flow versus how many of them stop at the next atom and drop to a lower orbit. And we see this in the test results of drive currents, wattages, and the resulting efficacies from this. So if we take a look at a 36 LED optical module and have it at various drive currents, let's compare 350 milliamps to 700, we see that 350 milliamps in this fixture, we're producing 5,871 lumens. At 700 milliamps, we're not doubling that to 11,600. We're only going up to around 10,500. because we have some inefficiencies that are created there, and that's reflected in the lumen per watt rating. We go from 146.8 lumens per watt to 132.9. And across the entire chart there, the columns as we look at them, we'll notice that the efficacy drops the higher the drive current. Now, if we move to the last three columns to the right, we're looking at the same optical system, the same drive currents, but in a larger housing, so you would expect that it would operate marginally cooler, and that's exactly what's happening here. So as a result, you'll notice that the lumen per watt efficacies, the efficiencies, are higher across the board with the exception of the 875 milliamp. And the reason for that is the 875 is not a tested case in this report, that it is a calculated case from the numbers that we get from the LED manufacturer. We haven't, the time that we did this chart, the testing on the 875s hadn't been completed, and so we just went with the numbers that we were given, and this is the result of it. But in actual test case, real world examples, you'll notice the larger housing operating marginally cooler, you have even higher efficiencies than you do in the smaller housing. This also helps us to appreciate that in the real world environment, on an 80-degree night versus a 40-degree night, our LEDs will be operating with less efficiency, less efficacy. If we take the same system that's operating outdoors at 40 degrees in the wintertime, you're going to have a little more light that's going to be coming out of it because the LEDs are operating more efficiently. And that helps us to get an understanding of why LEDs are an efficient source. Also helps to understand technically why we need so many test parameters in dealing with LEDs as opposed to what we used to do with either incandescent or HID lamps. We appreciate